is copy. And we should be rolling now. Let me just move this away. Okay, good. So once again, welcome to the 7th lecture. Today again in person, which I'm super happy to be about. And sorry for last week, it didn't work out. So what we're going to be talking today about is something called recurrent neural networks and a special kind of architecture which is called encoder-decoder. And how should we motivate this? So far, so we are working with language data. So tokens or sub-token units are going in and we want to do something with them, whatever the something could be, like classification or some other tasks. And the problem is like NLP, so multi-layer perceptron or some feed-forward network. The problem is that they need like fixed input size. They just need a vector of numbers, no matter how long the sequence could be. So, well, how do we deal with that? How did we deal with like different length of inputs to cram into like one vector size? There were a couple of solutions, yeah. The tokenization is clear, but let's take it for tokenized. So we have tokenized text and they have different lengths, yeah. We could take a maximum of the input we could expect and then make something with that. Yeah, that's a solution which we haven't used yet. We might use it later, but we use something much more easier, much more less fancier. Yeah. Yeah, back of words. So back of words is like you take every input token and just treat them and make an average of all the vectors. And then if you make average over 20 tokens, 30 tokens, 15 tokens, it doesn't matter, because all you end up with is one vector of one size. So that's how we deal with that. What you propose also some like we can take these vectors and just concatenate them together. So if we say like each document could be maximum 20 tokens, then yeah, we might just put 20 vectors after each other and that's maybe fine. But we did continuous back of word, so that's what the averaging. And something with limiting context, yeah, this is so in Markov property, we just basically said like, well, the sequence is always three tokens on the left, nothing else. Okay, but what we really want is, because what was the problem with back of words? What was the problem with back of words? What is the problem with back of words? Why back of words is bad? If you throw something in the back, yeah, the word order is lost. So we don't know. I mean, we have all this problem with dependencies between words, which are lost somehow. So what we really want is that we have some sequence of inputs, and we have some maybe fixed size outputs or maybe variable size outputs. We don't care yet, but the input is kind of tricky. So we need to do something about it. We need to build a network that can accept something between 1 token and 100 million tokens. Well, okay, what could be the longest document you work with? Could be 1,000 tokens maybe, or 5,000. It doesn't matter. So anything in between should be basically, we should be able to accept these different kind of size. So what we really want to build, some sort of network, is, for example, if we have 4 input tokens, we might want to build something like this, where these are vectors, or maybe these are vectors. Basically, these are the words. So 4 words, there are input to something which goes left to right. So this is interesting. Like we go left to right. Why should we go left to right? Why is left to right good? Like from first token to next token and to yeah. Because we read left from right, we think in a time scale like what comes after comes after. You know, well, like there's a natural progression. It doesn't make any sense to start from the end. So that's why we do left to right. So this is like the first kind of assumption we're having. And then everything else is kind of unclear. I mean, there is some flow information from left to right. Everything is somehow being taken into account. What exactly and how, I don't know yet. I mean, this is to be decided, but this is something which we would like to have. Because then if you add I don't know, if you just delete 1 token from here, so we can pretend this is connected together. I mean, it will work for 3 tokens, or we can add more tokens. So basically this kind of, variable input size could be of it. This is what we want to build somehow. The question is how to build this, right? And that's what we're what we're going to do with so-called recurrent neural networks. And we start with some sort of abstraction. So we have, again, the problem is that we have a sequence of n input vectors, x1 to n. So I'm using this notation to notate a sequence of different vectors, or a sequence of vectors. And each input vector, this is important. So each of the input vectors, these x's have the same dimensionality. So some d in dimensionality. So these are same size vectors, right? I mean, these x, all of them is the same size. This is interesting, or important, actually. Not interesting, important is it? What these could be, what these xi could be, well, typically, this is a word embedding of this token at position. But it could be anything, could be one-hot encoding, but word embedding is better. So what is word embeddings again? What is a word embedding? Static word embedding. What is it? Say again? You turn words into numbers, but is there any meaning of these word embeddings? Like, do they have some properties which makes them different from, for example, one-hot encoding? Because in one-hot, you turn words into vector. In embeddings, you turn word into vector. So what's the advantage of word embeddings? Yeah. You have similar words. Exactly. Similar words are somehow close into this vector space. So they have similar word embeddings. That's the property of word embeddings, which is very helpful. Yes. Sorry, can you repeat from the beginning? Sorry, I didn't get it. Yes. So the embedding space is unbounded, most likely. It could be like, okay, so what is in the embedding? So we have, so each of xi is a vector. I'm gonna write a column vector of size d in, which is the embedding size, which is typically 300 for word to vec. So 300 could be for word to vec, so 300 items. What's in here are just real numbers. It could be anything. These are not bounded. Typically, they are unbounded. Could be anywhere. It's just a vector space. Could be any numbers. Yeah. Maybe. Yeah, maybe cat and dog could be somewhere close in this vector space. Yeah. That's right. They're both animals. Yeah. Well, they could be close. I mean, just imagine if this were just 3 dimensions. Okay, so if this were just 3 dimensions, 3 dimensions is our Euclidean space. So we know 3 dimensions. This is our world. So here is a point which is a cat. Here is a kitty. Here's a point which is a tomcat. And here's some other completely different words. So these similar words tend to be somehow close in this vector space, and different words tend to be somewhere else. And this space is unlimited, unbounded, from infinities all over the place. This is what the word embedding space looks like. I mean, it lives in 300 dimensions, so it's more trickier to visualize or think about. Okay, so these are word embeddings which have the properties like these things are close together, and that's what makes it interesting for anything down the road. Good. And then we might have a single output. For now, let's start with something very simple. We have a single output, d out, dimensional vector, yn. And of course, so the input dimensionality and the output dimensionality, well, they don't have to be the same. It could be some other thing. What exactly the output dimensionality is, it depends on the task we're trying to model. It could be just a single number if you're doing like binary classification, so we turn it into 0 or 1 after sigmoid, or it could be a vector. So we don't care yet. And the recurrent neural network is basically a function from input to output. As anything we're doing with deep learning, it's just a function from the input to the output. So here it takes a sequence of input vectors and produces a vector. Okay, any questions? Sounds good so far. Well, in fact, so this was our RNN definition. In fact, it actually, by this definition, RNN is actually returns a sequence of outputs. Why is it so? Well, if we have, for example, 3 inputs, as we had before, so input sequence would be x1, x2, and x3, right? So these are 3 vectors coming into my network, and I have there should be y3. Okay. So the output at 3 is a vector, taking three things and outputting 1 vector. So, but the input sequence also, x1, x2, x3, also contains x1 and x2, which is like a subsequence of the first one, right? So this is a subsequence. And then, of course, we can take any subsequence, x1 and x2, for example, and output another vector. So this would be x2. I mean, this was a typo I need to fix later. So basically, for every subsequence, we can output a vector. Make sense? Like, if you take a sequence of things and output a vector, you can take a subsequence of things and output a vector, and subsequence of things and output a vector. Why not? I mean, this is the definition of RNN we have, which means actually that the RNN is outputting a vector at each position. So at each position y from all the inputs, it's outputting vector y. And we can call this sequence outputting function, very fancy name, like RNN star. This might be a little bit important if we're going to go into the details of the mathematical description, but maybe it doesn't matter, because if I just show you this example, what we have before, now we know what we're outputting at each step. So at each step, we're basically outputting the y vector for the previous sequence. So for example, here, the input was x1, and the output will be y1. Here, the input was x1 and x2, so we will output y2. And here, again, the input sequence was all those 3, because this goes through this flow of information of these functions, and it outputs y3 and so on. So basically, at each point, you're outputting some vector for everything which you've seen before. Okay? Make sense? That's great. What are these things? The blue ones and the gray ones? We'll figure out. I don't know, but we're taking step by step. So we have a sequence of inputs, and we want to output a sequence of outputs. That's awesome. So recap so far, for a sequence of input vectors x1 to I, we are outputting a sequence of output vectors. This could be, this is just a recap. So we don't know we still have question marks in this architecture. We still don't know what these kind of tiny little details are, but what could be these advantages so far? If you think about this, what are the advantages of this architecture? Yes. You have arbitrary input size. Yeah, okay, cool. There is something about the output. Okay, you're onto something. I mean, the input is like arbitrary size. This is great. And the output is somehow interesting because each output takes into account the entire history. So without the Markov property. It takes everything we just seen so far. So we don't have to limit our context into a couple of previous words. So if I just go back to this depiction here. So for example, the output at y4, it has all the information from all the previous inputs here. So all these inputs are flowing into y4. If we had, for example, the Markov property. So what is the Markov property, by the way, again? What is Markov property? Anyone? Markov property. You only look into a few previous words, not everything, right? So this is like first order Markov property would be you just look at the previous state, and everything else is irrelevant, like it's independent of where you are. And if we have like the 3-gram model or bigram model, we would basically look, if we were here, we would be basically only be able to look into like maybe 2 previous tokens. So we would limit the history. But now we don't have to limit the history because everything is kind of cramped into the current state. There is some flow of information. Okay, so the information flows from the very beginning to here. This is the very advantage of this thing. Okay, so this is the output. This is good. So what can we do? What can we do with these outputs? Like what can we do with these outputs at each stage here? So what these could be good for? Like think about it. You have a sequence of tokens which comes in, and for each of these outputs, excuse me, for each of these tokens, you can output some vector. You can predict some vector. So what these could be useful for? Say again? It could be used as a new input for what? Like you would go like that? Something like that? Maybe. Why would you do this? Keep this idea in mind. It will be useful later, not really right now, but there is something you're up to something. So it will be useful, but not for now because we have the input tokens and we can do something about it. So if this is, for example, a vector, we can turn it. We can run, for example, softmax of each of those. Softmax. What is a softmax doing? What is softmax good for? What is softmax doing? Yes. It's turning a vector into probability distribution, which we can use then for predict classification. So multi-class classification. Okay, so now we know we can classify each token into multiple classes. Because if you run it through softmax, we have probability distribution, and here we can put some loss, right? So what is the loss for multi-class classification? What is the loss function? This is very important. Okay, so this is the categorical cross-entropy loss. This is one of those important losses that we are basically using like two default losses. One is binary cross-entropy, and then then there is like categorical cross-entropy loss, which are the same things basically. So we can classify each token into something. So do we have a task where you want to classify each token into something? So we have a sequence of tokens and we want to classify them into something. What could be that? Yeah, but do you know the word? I mean, if I give you a text and ask you, write me a word embedding for each word, that won't work. So this is not a task. Like word embedding is just a means to the task. But what could be a task? So like putting a label to each token. We've seen this before. What is it important? Like, what do you want to do with each word in the sentence or sequence where you want to put a label on it? What this task could be about? Like having each label for each word. Yes. Yeah, you classify words into something. So what could you classify tokens into? Oh yeah, okay, nouns, words. So you can put like what is it called? Ooh, it's part of speech tagging. It's part of speech tagging. You basically say, oh, by the way, this is noun, this is verb, this is determiner, and this is noun, something like that. And now with this architecture, you can do this because you can classify each word into category. So you can basically do labeling. Sequence labeling is a task, which is part of speech tagging called POS. Oops, post tagging. Post tagging. We had something similar also for not part of speech tagging, but we also classified some words into categories. Not really. Not really. Do you remember named entity recognition? What are we doing in named entity recognition? Oh, yeah. I mean, we're assigning. So more concrete, like, do you remember BIO tagging? Beginning of entity, inside entity, and outside. BIO tagging, lecture number 1. We are classifying each word into whether it's beginning of name, for example, or person. Beginning of person, inside a person, and then O as like not the entity. Sequence tagging. Okay, so this is another task we can solve. Sequence tagging. Okay, remember this. Okay, so this is what we can solve with this. I mean, these Ys are important. We can plug them into use for further prediction. So plug into softmax, or we can be more fancier and even put like tiny little network on top of that, and so on. Okay, so far so good. So this seems like a good architecture. Like, well, but there is something still missing. Like, what is this, and what is this? We'll figure out. So let's start with this question. Like, we're passing information from one position to the next. So from the something at position I to position I plus 1. And for this, we're going to use something very simple, just a vector. So we call it a state vector. So a state at position I is just a vector somewhere. So we're passing vectors from one state to another. Just to show you the depiction here, so what we added here are these states. So these are the states. And this is just each state is a vector of some d state dimensionality. Bunch of numbers. This is how the information flows from one state to another. Make sense? Yeah, I mean, what else could you plug? I mean, the question would be like, what could be the alternative of passing information from one state to another if this is not just a bunch of numbers? I don't know, something much more complicated and unnecessary. So this is the simplest solution. Like it's just this thing is taking the input, producing some output, and also producing some state. And this is passed to the next one, which another input. And in the state, I mean, the state somehow remembers the whole history. That's the point. Like you're passing the whole history, you pack it into the state vector and pass from one stage to another. Okay? Any questions? Does it make sense? Okay. Could you implement it? So what you're shaking your head. You're saying like no. Oh, okay. Oh yeah. So we cannot implement it because we don't know how the heck are we creating the state and the output. Of course. I mean, without knowing this, you cannot implement it. If you knew what this is, can you implement this? Could you implement this architecture? Of course you could. You can implement because this is just a combinational graph. Nothing else. There are vectors coming in, so these are the inputs. Then there will be some function which does something, outputs something, it's passed to another function. So at the end of the day, this is again a function. If you remember multi-layer perceptron, like feed-forward network, well, this is something a little bit different, but not really conceptually different. This is like computational graph. You take input, you do some computations, a function, then pass it on the next function, pass it to the next function, and there will be some, maybe here could be some final output and final output state. It's a just bunch of functions together. So you should be able to implement it. I mean, there's no reason why you shouldn't. I mean, conceptually, it's not different from this very simple function we had in the first exercise, a plus 1 times b plus a or something like that. It's just more variables here. Okay? So this is just a combinational graph. Remember this, like everything in deep learning is just a combinational graph underneath, a bunch of functions together. So the question is, okay, so we have the states passing from one state to another. What could be this thing? Yep. Some initial states, exactly. Bunch of zeros. Why not? I think it's actually, yeah, it could be a bunch of zeros. So maybe you start with putting everything to zeros here, because why not? I mean, after seeing the first input, it will change into something more meaningful because you want to remember the first state, the first token already. So I would start with zero initialization, yeah. Or maybe something completely random. Why not? So initial state. Okay, any questions to this architecture? So far, so good? Okay, cool. So the last piece of unknown puzzle we haven't solved yet is that, well, what's happening here? What's happening here? What are we doing? Okay, so, well, this should be some, as I said, like this should be some function which takes what? So, for example, at this point, what this function takes, what does it take? It takes the vector of this token, right? And what else? I don't see any softmax here. It's not necessary here. It's yeah. And the previous state, exactly. I mean, basically what's here in the arrows, this is what is in the input for this thing. And this thing should output the y output and the next state. So what is this question mark going to be? It's a function. It will be a function. It takes two vectors and outputs two vectors. Right? Does it make sense? Like you change two vectors into two another vectors by some operation. What this operation is going to be, that's to be kind of decided. But basically, these are some functions on the input. So at each step, again, we have the current input vector xi and the vector of the previous state as y minus 1. And you were right. Who said like this all zeros? Okay, this is the initial vector state S0 assumed to be 0 filled. So you are correct. But anyway, so we have this previous, excuse me, the input of the current state, and we have, excuse me, the input of the current position and the previous state. And we want to compute the state at this position. So something we want to compute for first the state. And for this, we're going to use a function r. Like, why not? I mean, r is taking the previous state and the input and outputting a vector. Okay, so some abstract function r. What is it going to be? It's depending on the actual implementation. But there's a function doing r. So we have the state. What else we are missing? What do we need to do again? Yeah. No. What do you need to compute again? Yeah. The output. So can you guess what this is going to be? Like similar to this. Can you guess? Yeah. Function of the current state. Well, what is the current state? Is this I minus 1 or si? No, because it's gone. Si. So this would be si. This would be si minus 1, and this is xi. So what is it going to be the function again of for the output? What could be the parameter, the inputs to this function? Exactly. Exactly. Do you have a good name for this function? Computing outputs. Any guess? Wow. Okay. And I was wrong actually. I was wrong, and I was wrong. You were right. We're taking here. It is always correct, and we are already taking the. We're building the output on the state vector. You were correct. We're taking the state. Yes. Yes. Which means. Just let me come back here. So it's outputting the state, and it's using the state internally also here somehow to compute the outputs. Okay, why not? I mean, you can take the input, you can take xi and si minus 1, compute the state, and then compute the output. Or you can take the state and from the state compute the output already. So this is just a tiny little implementation detail, but basically the state contains all the information you need to compute the output at the current position. Okay, so we have two functions. One is for computing the state, and then using the state information, we have output computing function which produces the output vector. So plugging everything together, we end up with adding the R and O. So we have these R and O here. And that's how the information flows now in the recurrent network. So we have the initial state here. For each position, we have the input embedding, input token embedding, for example. And we have the output, and we have the state. And this is how the information flows from left to right in the whole network. The question is like how, what are the RNOs, and we'll get to that later. But this is like an abstract view on this recurrent neural network. So we have everything now for building this without, well, no, not everything. I mean, as I said, like, we don't know what the RNOs are, but maybe you will come up with a like very simple solution to these RNO, and you'll be correct, I'm pretty sure. But so far so good. So the recurrent architecture, advantages, variable input size, variable output size. Well, not variable output size. The output size is kind of corresponding to the number of inputs. So for each token, you generate something. You can predict something. You can do partial speech tagging. You can do BIO tagging. You can do many other things. So far, so good? Okay, I understand a strong. Oh, yeah, okay, sure. Yeah, okay, so what is X, what is Y? So X is, let me just come back here. X is input vectors. So X is number of input vectors, which are typically word embeddings. So you have tokens turned into word embeddings, and you have a sequence of them. Like the cat set would be three vectors. So this is the X. The Y is the output at each step. So at each step, you can do some output of those. And the output could be, as we just discussed, that you can classify each word into something. And the something could be, for example, part of speech text. So you would say the cat. So the task could be the cat set. And then I'm going to ask the linguist in the room to give me like the correct solution for the part of speech tagging. So what is that? The could be labeled as determiner. Is it correct? I'm asking the linguist in the room. Is it correct? The is determiner, the cat is noun, and set is verb, maybe past tense, something like that. So you could label each word. Does it make sense? Okay, cool. Good. So where were we? We have state vectors, adding these functions, summary. Okay. So at each step, we have the previous input and the current state, and we compute the next state and the output. And the functions, okay, so what is important? Like the functions R and O, of course, are the same for each position. This is some sort of like maybe simplification, but we want to make it somehow manageable. Because if these things were different for each, if R and O was different functions for each position, then we have troubles because if you add new token, like, well, which functions I'm going to add? So these are the same functions. They do something very similar way. They might have parameters, as we will see later. So, but these functions are the same for each position. And here's again the formulas. I mean, we talked about them already. So this visualization, I mean, now the only difference to things we had so far are the parameters. So what's the name of this fancy Greek letter again? Theta, yeah, theta. And theta is for parameters, typically in machine learning. So we have a bunch of parameters, and of course, these functions, since these functions at each step are the same functions, they might have parameters, such as weights and biases, and they should be the same for each step. Because these functions should be same for each step. Why is it so? Why want to have the same function for each step? Like if we are taking the previous input and go to the next state, we want to have this the same, behave the same behavior basically in each step. Why? Any idea? Like why should this be a thing? So think about it like that. You might have some input of tokens like the cat set. And the cat set is a phrase that, well, having seen, no, like, it's a bad example. No, that's a bad example. I'm sorry. Because what's going to happen should be independent of the position. That's like, so if you're at position, if you go from position x3 to x4, it should behave in a similar way as if you were going from position x1 to x2. Like maybe there's more previous input, previous, let's say, previous history. But at this point, you just want to have the same parameters to move forward. Because if you have, well, and practical reason is also that the number of parameters would basically grow with the size of with the length of the sequence. For example, if you have like only 4 token sequence, you would have like 4 different parameters. And then if you have a sequence of length 10, you would need like 6 more parameters, but maybe you just never learned them because you only saw parameters for length number of size 4. So that's why we can basically keep the parameters for each state the same, and we share them. If we convert it into a linear model, I don't know what you mean by linear model. Yeah. But so we haven't talked about whether it's linear or not. It won't be linear, most likely. I mean, there are no functions here specify it. I mean, this is just how we have functions which just take the previous vectors and do some vectors. These functions could be linear projection, there could be nonlinear projection, there could be something. So this is how I think about like linearity in the models. So if everything is linear, if all the functions here are linear, the output will be linear, and it's called of like, it could be like a linear model. But we know that linear models cannot solve nonlinear problems, like XOR, for example. So this is first kind of addressing your linear, nonlinear question. But, well, the gradient will be important, but for a different reason. So there will be something with the gradient, but the gradient doesn't have to do, it's independent of like whether the parameters are shared. So sharing the parameters means like you can basically have really variable size inputs, and then you still be able to learn some parameters, how to transfer from one state to another. All right. So this is also called like unrolled abstraction of RNN. And note that these parameters are shared. So they are same for all positions. Well, these parameters are going to be, maybe some weights, obviously. Yes. Yeah, it is. Yeah. If you say, for example, okay, here, just an example. So there's an input, let's say there's just 3 tokens input, and here's some output at the last. So, and I'm guessing, and I'm almost certain that the output here will be different for the cat set and the set cat. These 2 sequences will most likely give you different output at the last state. If you throw this into back of words, bunch of averaging word embedding tokens, these will be the same. So this is why this ordering matters now here. And that's the problem. The first slide was like, we're trying to tackle this problem exactly. So now you're in picture. Okay, good. So this is the unrolled visualization of RNN. And this is how it actually looks, like how the functions are and how it's actually implemented if you do like the computational graph. When you think about it, you can do some recursive abstraction of that. Basically, because at the end of the day, there is at I position, there's the input, there's a previous state, there's a current output state, and there's a current output. And there is this dashed arrow is basically that you treat this then for the next iteration as the previous state. So this is like the rolled version, like the recursion is shown here as just a simple one block of these things. But when I think about RNN, I just think about like the unrolled thing, because at the end of the day, this is unrolled. You have number of inputs, and this is the flow from left to right. Yes. Yes. The theta is some parameters which will be important for the function. So it's some sort of weight, because we're kind of anticipating that these functions will be parameterized. Because look at this. Let me just kill all the parameters. So now, this is fixed. This is given, right? Input is given. Static word embedding is a bunch of numbers. This is constant again. This is again constant. This is given. This is again given. This is constant. This is all zeros. What do you want to train here? Like there's nothing to be trained. Everything is constant. Right? So you need some parameters to be trained to do your task. So these will be the theta somehow. And I'm using still the same colors. You also anticipate from the colors. I'm using the green color in the lectures for trainable parameters. So it's also like saying like this will be actually learned. The rest is just input, and this is 0 state. Okay, does it answer your question? Not really. Okay. Oh. So let's keep this question for when we show the first implementation of this R and O. You will understand like what these weights are. Okay. So, but before going into that, what can we do now with the network? So we are talking already about the sequence labeling, but maybe we can actually, so, right, this thing, this is what we had so far, right? I mean, this is the network, inputs, and everything. So this is just copy pasted here. So we have, and in the last output here, we have some sort of like a vector representation of the whole sequence, right? Because all the previous states are integrated somehow or crammed into this one vector. And if you put a softmax or sigmoid or multi-layer perceptron on that, we get some output y hat. So output y hat could be a probability distribution or just a single number, which is typically also probability. And what this could be, what is y here? What could this be? Yes? This is the gold label, okay? This is the gold label. And if you look at this architecture, what this gold label could tell us? What could be this gold label, for example?
For example, sentiment analysis.
Mm-hmm.
That the axes are like the vectors of the sentence.
Right, yeah.
In the end, you want to see if the sentiment is captured correctly or not.
So this Y could be exactly the label for the entire sequence. So this could be, for example, the sequence is number of tokens, so a movie review, for example, and the gold label is positive or negative. Is the movie review positive or negative? Right? This is like basically sentence classification or document classification. So we can use this for document classification, and the L is obviously some sort of loss. And this could be multi-class classification into what could be like topic classification, sports, business, and stuff like that, or it could be sentiment binary, it could be sentiment neutral, negative, positive. So because then we know that in this vector, the whole sequence, the whole input will be stored somehow. Okay? Any questions? Good. So this is, and again, like the cat set and the set cat will have different final vector representation, and which is make it much more powerful architecture in a way than just a backup words. So this is the final output on the final kind of vector here. Any questions? Good. So then we have also the network as a so-called transducer. And we had this example already. So don't be scared of this, like it looks crazy maybe on the first side, but this is again what we had before. So we have this architecture again, this R and N. So these are input words, and we are producing output at each position, right? So this is what we had before. And as we discussed already, we might put this vector through some softmax or multi-layer perceptron, some sort of, maybe softmax is the easiest one. So we just softmax this vector, and at each position we have also gold label, but these are now indexed with a position. So for each word x1, we have y1, x2, we have y2, and so on. And again, we had this example already. So this is like for sequence tagging. So at each position, So at each position, this could be, for example, the part of speech tag, or it could be the BIO encoding, BIO named entity recognition tag, or something else, right? So this is what we have. Each token is classified into gold label. So for example, the training data would be x1 is D. Well, no, not D. The x1 could be some sort of embedding of D. x2 could be embedding of cat, and x3 could be embedding of set. And then y1 could be one-hot encoding of what is it? The is determiner. So determiner So one-hot encoding means 0, 0, maybe here's 1, maybe 0, and so on. Y2 would be one-hot encoding of noun, because cat is noun, right? So this would be maybe 1, 0, 1, and zeros. And Y3 could be one-hot encoding of verb, because set is a verb, which would be something like that. This would be like the full specification of the Y's and X's for this part of speech tagging. Okay, makes sense? Okay, so here we have a loss, but then of course, I mean, we are optimizing, we can optimize or minimize only one single loss, right? We cannot optimize like 20 different losses. So what do we, but now each of the position has its own loss, which could be some binary cross entropy or categorical cross entropy. So the easiest way how to minimize a number of losses, it's to minimize its sum. So we can basically we can also take the average loss, or we can take the sum of the loss. Because if you're minimizing sum of the loss, you're somehow minimizing each of these losses in a way, right? Yeah, you do, I guess so. Okay, so this is the part of speech tagging now in exactly detail how to deal with these with the output at each position, the yi at each position, where the gold label is coming from, and how to do the loss. So now it should give you a hint, like if you really want to implement this thing, still without knowing what R and O's are, but this could be like the output layers implementation, like how to plug the gold labels into this architecture to do part of speech tagging. Okay, questions?
Why can't we just compute the left at n? Because why more would be the result of the whole sequence.
Yeah, that's right. I mean, the loss. So in this, you are right. I mean, here, if you want the full sequence to be in one vector, and you can say, so for example, here the gold label will be for sentiment. It would be if so. Let's say the gold label is positive, which we represent as one-hot encoding over 3 classes S1, 0, 0. So far, so good? Okay, good. Now we are running overall, we're taking into account all the inputs and producing the vector y hat. So the y hat could be something like, I don't know, some after softmax. So this would be a probability distribution. So maybe 0.80 and then 0.1 and 0.1. This could be the prediction. This could be after softmaxing. This could be this prediction of the network. So it's giving 80% probability of being positive, and the rest is somehow less probable. So far, so good? Yeah, and then we take these two into the categorical cross entropy loss, which is the sum of probability of first times the logarithms of 1 over probability of the other, sum up together. And you compute the loss. Because you know the label for the entire sequence. Do we know the label for the entire sequence here?
The sequence they are, and then compare. You know what I mean? Like instead of checking the label for each of them, checking the tag for each of them.
Yeah. Yes.
Make a list of the actual labels and then just compare the gold.
Oh, okay. So you would say what you're proposing is, let me just come here. You would say, I have the cat set, and I want to generate determiner, noun, and verb. And I don't care about like outputs here. I don't care. I just want to generate a list. You can do this. You can do this, and we will have an architecture later today, for example, encoder-decoder for generating text, which is exactly doing what you want. Though the task is much harder here in generating text than just producing the output for each, because now you can supervise you know the loss for each token exactly. So there is one-to-one correspondence for part of speech tagging. If you want to generate sequence, then I mean, in a way, you're generating a sequence in a way, but the supervision here is very, very concrete for each of the input. You know the gold label, so it makes sense then to have the supervision of each label because there is the maximum amount of information. If you would use the encoder-decoder for that, as we will see that later, then the flow of information will be much harder because there will be long dependencies between the output and the input. Okay, that's a good question. Keep this in mind. Okay. So we have left to right, and there's also something called bidirectional recurrent neural networks. And this is a simple idea. So you have one RNN from left to right, and you can have another RNN from right to left, and then take the input as a concatenation of these two. What does it mean? So it could be interesting for, well, not for, well, maybe for document classification or, well, for anything we have, like even for sequence labeling, if we don't care about the left to right ordering. So if you have the full document already, you have the cat set, which is a positive sentiment because cats are cute and they're just, if cat sits somewhere, it's like very, I don't know, this is not an example for sentiment analysis, but let's say if it were. So then you would run left to right and have the vector here. And then you also run RNN right to left and have another vector here. And just take these two together and concatenate together, and this would be your final vector for your prediction. You can do this. I mean, two LSTMs two RNNs, one left to right and one right to left, and you can take the output here and maybe concatenate for something else. The advantage of that would be you have not only left to right dependencies, but also right to left dependencies, which might give you more advantage of having all the information. Yes. What is the meaning of what? What is sum of losses? Okay, so what is a loss? How do you understand loss? This is important. Like, what is a loss? Yes, it's a function which takes a network prediction and the gold standard label. And it's compare how off you are in a way, like how bad are you predicting. Loss is a function from these two inputs into a positive number. So something, it should be more than 0. So loss is never negative, from 0 to infinity, for example. So this is a function which gives you how off you were on one example. And here we have multiple examples at once. So the loss here, this is one loss, another loss, another loss, another loss. And you want to optimize everything at once. You want to find the best. You want to train a network that it's able to sort of like jointly for the whole sequence predict the tokens, predict the tags of that. And you can sum up the losses together. I mean, it's a function. The loss is differentiable function, and sum of differentiable functions is also differentiable. So the sum function, basically, you know how to make a derivative of the sum function, which means you can plug this together, and everything which is blue here is a differentiable function. So you have one single output loss, which is a sum of these token losses, and this gives you like a one single final loss which you need to optimize. Why? What? So sorry. What was the question? Yeah, of course. But if you minimize the sum, then you're also minimizing the terms. Well, I mean, okay, so it's why is it sum? I think it's like empirically, it's the easiest thing to do and it's fast enough. If you do the average, you can minimize the average loss overall tokens. That's fine as well. Whatever differentiable functions for combining number of losses suits you, you can try out, and it just might work. No. Accuracy is a different metric. Like the accuracy doesn't have to do anything with loss. I mean, there's some, they correlate. I mean, the lower the loss on your, and also you're computing loss on training data. You're minimizing loss on training data, but you're computing accuracy on your def data or test data. So keep in mind, like having loss minimal is good, but it doesn't tell you how accurate your system will be because these metrics are different. We want to minimize loss, but it's just saying like, am I fitting the training data well? And then you have your model and you compute your accuracy, blue score, F1 scores, whatever you want to do in different metrics. Exactly. No. Cross function could be mean square error, but we're using categorical cross entropy, which is another line. Categorical cross entropy is, what is it? If you have k categories, it's probability of so y hat at position I times log of 1 over probability of the gold standard at position y as well. And I hope I'm not mistaken with the y hat and y. I think it's correct. This is the loss function, which is, I mean, you could do mean square. So you can do like y hat at position I minus y at position I squared and minimize this and sum up. You can do this as well. Yeah, it's just different, it behaves differently. So cross entropy loss penalizes, because of the logarithm, it penalizes more the misclassifications. Does it answer your question? No, it's just a different way how you minimize the function. This is just a different way how you penalize the misclassifications. Like mean square error has some properties, and cross entropy loss has different properties. And if you look into the details, I mean, if you're interested, I think like 2 years ago on one of the lectures I had, if you look up the slides on GitHub, there is a comparison of mean square error and cross entropy loss, showing that cross entropy loss actually penalizes more the misclassifications, which means it will be bigger loss, which means the gradient will be stronger to make the updates if you really want to nitty-gritty details. Okay, good. Okay, we need to move on. Oh, we need to move on. What's inside RNO? Okay. Now we go to the architectures. Simple RNN. Okay, so how could we? Okay, we have some parameters. We have vector, and we have vector, and want to do two vectors. How do you take two vectors and make another vector? This is the simplest solution ever on the planet. You have vectors, maybe like that, maybe like that, and you want to make a vector. And let me do something else. Let me do just row vectors because we're working with row vectors. So we have xi, we have si minus 1, and we want to do, for example, yi. How do you go from one vector to another vector? You cannot change the dimension by adding them. And these have different dimensions. That's a fair baseline, but it won't fly. Anything more advanced, but still baseline. How do you go from one vector to another vector? Yes. Second? No. It's a vector. You have one vector and you need another vector, and they have different dimensions. How do you do this? Okay, so let's say this is size m, and this is size n, and this is size k. If you concatenate them, you can do this, but you cannot choose n. Yeah, multiply by matrix. You just multiply by a matrix, and you get a vector. What is it? What is multiplication by matrix? It's a linear projection. You can project one vector to another vector by a matrix, by a linear map. This is a simple solution. Okay, so what do we do about SI? So we multiply by another matrix, and maybe then sum them up. Maybe there will be plus. This is the simplest solution I can come up with. which is exactly this here. So we have two matrices for projecting, for taking the previous state and projecting into something else. We have another matrix for taking the input at position y and projecting into something. And what is the B? It's a bias, some sort of bias vector. Okay, fair enough. So we can make a linear projections of the previous input, previous state and the current input, and add some bias. What this G could be? So we have a vector and then we use some vector G on that. What could that be? No. Ooh, no, gradient. No gradient, no. The gradient there is no gradient today. Gradient is like how you minimize, how you compute partial derivatives and make minimizing the functions. We're not there. Yes. Some nonlinear function, exactly. Non-linear function. Why we need a nonlinear function? Why we need this? Otherwise, everything would keep linear. I mean, if we have linear projection all over the place, everything will be linear at the end of the day, and we won't solve the problems we really want to solve, which are nonlinear in the nature. So this is some nonlinear function. An example of nonlinear function? So there's an example. I'm looking at you. Yes, I mean, you propose nonlinear function, so give me one. You know what? I mean, you can actually do softmax here. That's not a bad idea. I mean, you could do softmax. It might actually work because softmax takes a vector and produces a vector, and it's nonlinear. That's a good point. You could do this. Something even simpler. Sigmoid, yes. Sigmoid, but sigmoid takes one input and produces one output. Sigmoid it doesn't take the vector. So how do you do this on vector? Ooh. Yes. Component wise, yeah, you take each item on the vector and just run sigmoid on top of that. Sigmoid, let's call it like per item. So if you have a vector, position 1, 2, 3, 4, 5, and you want to run, and you typically say, I'm going to run sigmoid. This is sigma. You end up with sigmoid of 1, sigmoid of 2, and so on. So you basically, there's a very fancy word in NumPy for doing this, like element-wise. What was it? Broadcasting. You broadcast the function sigmoid over all the items. Okay, so this is a sigmoid. Cool. And now, so we know how to compute the next state, just linear projections of the previous and current. And the easiest way of doing the output is basically identity with the hidden state. So we just say, okay, the SI and YI, the output and state are equal because this is the simplest solution. I can output the hidden state, the state will be the same as the output. Why not? This is the simplest thing I can do. Agree? Yes. The same, like really equal. Like you say, okay, I can compute SI, I can compute this hidden state, which is a 2-matrix multiplication and sigmoid. And if I want to compute the YI, I just say YI equals SI, just the same vector. So basically here we would have these would be the very same kind of node, like same value. Like conceptually they are different, but we would say these are the same. This is the same vector. Okay. Good. So here's some more. These are just to make sure that you understand the dimensionalities of the multiplications, because multiplying by matrix is a linear projection from one space to another space. So the dimensions have to be, they have to match. So you have to know what a matrix is, the dimensionality is, so you can take a vector and get another vector. And the G, okay, so we had a sigmoid. It could be also 10H, or ReLU is also like one example of nonlinear function. Like ReLU is the knee, basically. So this is the so-called Elman network, or simple recurrent neural network. And now you have everything. You really have everything now to implement the whole thing. You know how to compute the next state. You know how to compute a loss. It's a computational graph. So if you try hard enough, you should be able to build it really from the very kind of primitives we're talking about. There's nothing preventing you from doing so. It will be a little bit, complicated to really fit the data in it if you have multiple different sequences, so to do the unrolling correctly and so on. So like implementing RNN from scratch is somehow like, I guess it's a lot of hassle. So I have never tried actually because it looks like awkward, all these different, but theoretically it should be possible. Like it's easier to work with MLP or feed forward where you have like fixed vector size input. You build your architecture and call it a day. Here you have to unroll for each sequence to make the network unrolled to really matching the inputs. But at the end of the day, it's just a computational graph. So the problem here, and somebody mentioned the gradients, I don't know, somebody mentioned gradients, is that so what is computing the gradient? I mean, you want to compute here is the output vector, here is again some sort of loss. Okay, so we are minimizing the loss with respect to all the parameters. So for example, theta 1 could be some weight somewhere. And now the flow of the gradient, so if you remember the chain rule, we're making a product, we're multiplying all these gradients back through the network. So we're multiplying this gradient with this gradient, with this gradient, this gradient, this gradient, back to this gradient with parameter theta 1. We're multiplying a lot of things. The deeper the network is, or actually the longer the sequence is, the more multiplications you're going to have. And the trick is, what happens if you multiply too many very small numbers? Second? It's going to be 0. That's called like vanishing. So it's going to be very close to 0, and then eventually it will be 0. Which means the deeper the network, because I mean we can see it as a deep network or long network, but there's from the loss where the information is about the supervision to the parameters which you need to update. So this partial derivative will be a long chain of multiplications, and the longer the chain is and the smaller the gradient, you can vanish the gradient, and the gradient will be 0. What does it mean, a 0 gradient? Well, exactly, you cannot perform updates, but it means that this parameter won't be updated. It will just keep the same. So you won't learn anything about the parameter. You cannot change the parameter, and you cannot improve your network to do some better, to minimize the loss. So vanishing gradients or 0 gradients, bad thing because you cannot learn anything meaningful. Okay? And now we understand why. Because the length and the possibility of multiplying so many small numbers will lead to a very small number. Everybody's with me? Okay, cool. Is there something like the opposite of vanishing gradient? Yes. Exploding gradient, because you've heard it before, right? Exploding gradient. Okay, yeah, it's a term. Exploding gradient is the opposite. If you multiply too many very, very large numbers, if your gradients are super huge all the way down, then you multiply big, 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 and then you have like overflow of numbers or gradient. If you have infinity gradient, what you gonna do? Nothing. I mean, it's kind of bad, right? So, and that's a problem for this standard Elmer network. So in deeper nets, and especially in recurrent networks, this is hard to learn, to train because of these long-range dependencies. So we need a solution for this. And one solution, which will look like super complicated, but it's kind of empirically very strong one, is using gates. And let me try to motivate this. So we can see each applications of this function R. So the R is computing the next state, right? So the next state computation is this R function taking current input and previous hidden state, and it's doing this multiplication. What is it actually doing? It takes the current oh, we call it memory now. So the state, we turn it into very something fancy, a memory vector, reads the current input, operates on them in some way. Here it's doing these kind of fancy linear projections and non-linearity, but it's just do something with this and writes the result to the memory at, well, as state at this current output, excuse me, state at this current position, and we call it a memory. Oh, this is interesting. Yes? Well, the current memory, I mean, we just refurbish the name state and call it memory now. It's a vector. Like SI represents, it's a vector. It's a vector of dimensionality V state. A bunch of numbers. Now this is my horrible writing. This is a vector. Like, I mean, look here. This is a state, but now we call it a memory. Why do we call it a memory? Why do we call it memory? Yeah, but what do we call it memory now? It remembers everything from the past. We can call it a state, we can call it a memory because it somehow remembers everything what we've seen before. So now we start calling it a memory and we say, okay, actually what we're doing in this R function is that we update the memory. So we tell the memory what should be stored in it. We say like, oh, you should remember everything from the past and here's how you update your memory. This is our change of perspective. But so this is, if we say like the vector is a memory and we can store information, as in the positions of this memory, we don't control the access. So at each step, the entire memory is read and the entire memory is written. Why? I mean, we take the previous memory and we output a full memory. So we take a vector and change everything in it. It's like a memory for the next step. It's like if you take your entire memory in like a computer and just not erase something which is important, but erase everything and just put everything in it again. So do you see this analogy a little bit here? Like if we talk about memory, we're storing something into the vector, which is important to remember from one state to another. Does it make sense? So let's have a memory vector of dimensionality D and the input vector of the same dimensionality. So this is like very simple example. Okay, so bunch of numbers and bunch of numbers. And let's have also a binary vector, which we call a gate. Why gate? You will see just in a second. And these will be binary numbers. So for example, if we have 0.1, 22, and 3 would be S, and X would be the same, like -2, 3, and I don't know, 21 numbers. And the gate would be the same dimensionality. Gate would be maybe 0, maybe 1, maybe 1. Okay, so this is an example of the state or memory, input, and the gate. What we're gonna do with this, so that makes sense. I mean, this is just two vectors and binary vector. Why is it important? Is that there is a thing called Hadamard product, which is this very fancy circle thing, but it's just an element-wise multiplication. So if you have two vectors and want to multiply them element-wise, you just, so x1 and x2, then you just multiply each of those together and make a vector out of it. Okay? Element-wise multiplication of two vectors. Very fancy name, Hadamard product. So if you want to show up somewhere in the bar, say, oh, yeah, Hadamard product, of course. I don't actually know anyone who's using this seriously. But anyway, multi-wise multiplication. Good. And now we're going to do something very awkward here. We're going to take the input and multiply it by the gate. And then we're going to negate, make a negation of the gate and multiply by the state. What does it mean? Okay, I do have an example. So it reads the entries in the X corresponding to ones in the gate, right? If we multiply this only by ones, then everything which is in gate is 0 will be forgotten. and then all the other positions will be kept from the memory. So just an important operation here, like the operation here is modulo 0, and you will see why. So here's the example. We have, so this is x, this is our input, and this is the state. So we take the input, and this is the gate, right? Gate is 0, 1, 0. So 0, 1, 0, 1, 0 is the gate. So we're gonna take a gate and multiply element-wise with the current input, which basically means everything which is 1 will be taken and everything else will be 0. Okay? Like multiplying by binary vector means you just take the positions where it's 1. So just the second position will be kept. So far so good? Good. Hadamard product, very fancy thing, but you just take element-wise multiplication. And now here we take the 1 plus g, which is basically negating the vector because we're in modulo 2. So everything which has been 0 here, it turns out into 1 and vice versa. And now we're multiplying the state with this negated gate, which means everything which is 1 will be kept, and which is 0 will become 0. So, as you might see, of course, we end up with two distinct bunch of numbers complementing each other. And once we're going to sum them up, we end up with 8, 11, and 3. So what we did is just, so the gate is sort of like a mask. You mask one vector and take only those elements where you have 1 in the gate, and then you negate the mask and take the complementary thing from our state. So what is it doing actually here is that it keeps something from the state or from the memory, and it adds something from the input. What exactly is it doing is determined by the gate. So the gate is basically telling me, this is the new input, put it in. And the rest, where the gate is 0, just keep from the state, from the memory. Okay? Good. What's the problem here with this? The problem here, I mean, it could be used for gates in RNNs, but these gates are not learnable. I mean, this is like hard-coded 1, 0, 1, 0 vector. So and there are also no differentiable in a way, like how do you take a gradient? How do you minimize through this thing? Oh, it's kind of hard. So what we're gonna do is that we replace these hard gates with something which is like soft gates. So something which is differentiable and you can learn as a parameters. This is the idea for the next architecture we're gonna talk about, like soft gates, learnable gates. And the gates are saying, I have a bunch of numbers, this is my memory, and I wanna keep something from the previous state, and I wanna update the other state from the current input. This is like controlled updating of a memory. And I wanna learn, now I'm not telling like, oh, first 4 positions will be updated and the rest will be forgotten. No, I wanna learn which positions will be updated and which will be kept based on the input and the task. So this is very cool. Like learnable gates. I wanna learn how to control the memory. I wanna learn functions which are almost binary, but can be differentiable. Okay, I need to speed up. So here's the thing. So there's a very famous architecture called short-term memory, LSTM, and it's been super popular, but now it's not really super popular. But sometimes you see it for some other tasks, not in NLP anymore that much. But for modeling sequences, it's still kind of interesting. And it's designed to solve the vanishing gradient problem by the gating mechanism. How it's exactly doing is that it takes the state vector and split it into 2 halves. And 1 half is treated as memory cells, and the other half is working memory. These are working terms. I don't think we need to really know the LSTM architecture because it's kind of complicated. And if you need to implement it, you just look it up. But it's like interesting approach. And the memory cells are designed to preserve the memory across time. And there's this differentiable gating components. So what do we have? Memory, hidden state component, and the gates. Okay, we talk about gates. So LSTM has 3 gates which makes it more complicated. And there's an input gate, forget gate, and output gate. And by the name, you can tell like the input gate is telling how much I can take from the input. The forget gate, it's telling like how much you need to forget in your memory. And the output gate is telling like how much you wanna filter out the output. I'm gonna go through the, so if we want to go really fancy, I could go through the architecture. I'm gonna do it very quick because I don't think I mean, you can take it on your own because I don't have to explain the graphics. Because at the end of the day, it looks very complicated, and it is very complicated in a way. So I wouldn't want to implement LSTM by my own from scratch. Maybe if I'm really pushed to, I could, but I don't want to do this. But here we have the previous states split into the two vectors, two halves. And I'm gonna just scroll through and not gonna talk about this because this is something you can look it up. I don't want you to remember the architecture of LSTM because I think it's not super important. But then you will see like just that's how complicated it is. So at each point X, we're gonna make some projections here into so-called update candidate. Then we're gonna do the forget gate, also some linear projections, right? I mean, the important part here is that there are just linear projections and some nonlinearity, which is tangos hyperbolicus most of the time, I guess. Forget gate, then we have the input gate again. We have updating the memory cell by the gates here. So this is similar to what we saw before in the gating mechanism. So this is the Hadamard product. Basically, these F's and Y's are mostly zeros and ones, mostly close to them. I mean, these are not binary 0 and 1s. These are somewhere close because this is like should be differentiable. So this is output of some function such as sigmoid. So it puts the numbers close to 0 or close to 1. So this is the gating mechanism. Then there is the output gate, again some linear projection, and there is a combination of the output gate with the previous cells, and it gives you the output at state and the next hidden state. So it looks super complicated because there are 3 gates and they're doing a little bit something different. There is a bunch of parameters, lots of dimensions you need to keep into account if you really want to keep this, if you really want to know what is it doing, and a lot of indexing. So we can keep this whole thing as not a black box, but as a single kind of layer and simplify and saying, okay, there's an LSTM layer or LSTM cell with all these input gates, forget gates, output gates in there. Eventually, this is again a recurrent architecture. So this is RNN. We have the previous state, we have a current output, and we have the next state, and we have the input. And here there are the functions doing the output and doing producing the output and producing the next state. This is much more complicated, and I mean, look at this and compare to the Elmar network here. Like this is super simple. What was it? This is very simple, just a single projection, very few parameters and things like that. So the LSTM is much more complicated with introducing these gates, but eventually it's again a building block of recurrent architecture. So once you implement this and it works, you can just take them together and just everything will work. It's just computational graph if you don't make any mistakes. But there are just much more many parameters. So all these weights for the forget and input gate. And we also ignore the bias term and so on. So far so good. LSTM. I mean, you should know about this, but I don't think you should, remember everything in there. It's not important. There are better architectures now. So in the last 5 minutes, I'm gonna address something which is maybe we'll make it in 5 minutes, hopefully. So now the problem is that we have variable input size, like we can have multiple different sizes of inputs, like tokens, but maybe you want to have like output size also differently, because now so far we have each input has its output. So for part of speech tagging, BIO tagging is great, but there's tasks where we need to generate text. So let's say we have outputs which have different kind of length. So what could be what could be task where we want to do like different outputs? So we have an input sentence and the output sentence has different length. A task. What is a task? When you generate language sentence and the output will be different. Yes. Classification is like you have a vector and it's always the same. You classify a vector. Machine translation, because you take text and you output text. Can you do machine translation with the network we had so far? Oh, badly. So let's see. So we have actually, so here's the question. Is the translation correct? Ik bezoek again deep learning Vorlesungen. Is there a better translation? Sounds legit? Good. How many tokens we have here? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. If we take this as one token, we have one token here. So, okay. So we have different sizes. This is not just a bad example, but anyway, I mean, you get a gist. Like the translation is like generating text, which is not the same. So what can we do is tokenize the input, take the word embeddings for each word, and use, for example, LSTM to encode sequence of tokens. And then we need to generate token sequence in the target language. So the generation is kind of tricky now. Okay, so how can we do this? So we can do multi-class classification over the target vocabulary. So basically, for each token output, we predict vocabulary, we predict the probability distribution of vocabulary. And then, as in language model generation, we just take the word with maximum probability, maybe, or maybe draw the word from the probability distribution. There are different ways how to take the word out of this. So the problem so far is that no. Let me just generating, no, this is bad. Just forget this slide because it doesn't tell anything. We need something which is called sequence to sequence. So, because so far what we were talking about was this sort of, or encoder-decoder. So far we are talking about this encoder part where we have an input and it goes to LLM cells and there is this, recurrent RNN cells and we generate a final output. But we are talking only about like, how to produce here the tokens. But we want to have a different number of tokens. So for example, there could be 4 tokens as the output. And that's tricky. So we have 2 parts of the network. One is the encoder, which takes the entire input sequence. And the second is the decoder, which generates the output sequence. And they have different sizes. It's very badly written, but the input has a size of n, and the output has size of n head. Wow. Why? Could be m, whatever. Different lengths. So these two, and this is like, as you see, it's left to right. I mean, this looks like a recurrent neural network, and we will utilize recurrent neural network to do this task. But the question will be, what are these inputs in the second part going to be? Okay. And maybe these 2 things have they have separate parameters. So the parameters of theta here are different from the theta here. So theta encoder and theta decoder. Why? Well, because you want to learn something else, how to generate a representation of the input sequence, and you want to learn something else, how to generate tokens in the target language, for example. So there are different parameters. So how do we initialize a decoder state? Is that we take simply the last encoder state or memory and put it into the neural network. So this will be the decoder state. So here we take the last output of the encoder and put it into the decoder state. So the decoder can really have a different kind of little bit of the architecture. Typically we have the same architecture for encoder and decoder. Then how do we stop generating with the decoder? So how do you know, maybe because you're generating words, how do you know you should stop generating? And again, as we have in this language modeling task, like with the Ngram language models, we just say, okay, there's a special token called end of sequence. And then we say, okay, now we stop generating text. Or when we exceed a maximum length. The question is, what are the inputs of the decoder, right? I mean, we know what the inputs are of the encoder. What is the input for machine translation here? Any guess? Yeah, the tokenized version of the original sentence, for example, if you do English to German, so in English. So these are English tokens. We know how this runs now. This is a recurrent network. We have this final state here, which comes here. and we know how to navigate from between these states. But what is going to be this here? What is the input to the decoder? Because it has to be something. Because if you use our notion of recurrent neural networks, we need input for each state. Well, so what this going to be? What could be the input to the decoder? Empty vectors? Could be empty vectors. Well, I mean, it could be empty vectors. We don't know the words. Could be empty vectors. I think it will break maybe empty vectors, maybe. So maybe something else. Yes? Random? Okay, so maybe you're onto something. I would say like here, the first thing could be a very special vector called the beginning of sentence. It makes sense because you're here and the input is like, well, I have no idea. So I'm saying like it's beginning of sentence. And here in this vector, I have the full input sentence in one vector. So this is good. And I can start to generate the first word to be of the translation. But what is going to be the next one here? So it's not going to be 0. Yes? Like that? Yeah, this is like 1 time step back. It's going here. And that's correct. That's a trick. You're basically saying, well, I don't know what to put here as an input, but the best input I can have is the previously generated word. Makes sense because everything, all the information is transferred in these hidden states. And the input is the previous words, which give me more information about what to generate next. This is how these things work. Like typically you take, it's called autoregressive. Autoregressive, which means you're eating your own output in a way. You're taking the previous output and putting here. Now, does it make sense? I mean, why it works? Well, partly magic, partly maybe some theory, but it just works. And then, so this is the input, previous output of the decoder. And then we can use one thing. If we know the gold standard labels, like what could be? I know a better example. I love you. And then we know the output should be ich liebe dich. So then we might, instead of, so if this is generating the first word and it generates something else than ich, maybe dir, we might want to, in training, we might want to put it here in the next vector, like the generated word. That's what we were doing in inference. But in training, we know the correct word. So we want to put the correct word instead of the generated word here to give more kind of signal what this thing should be translating. So it's called teacher forcing. With some probability P, we use the correct output. So instead of what's being translated and maybe wrongly, so for example, instead of ich, we can take the correct one and teacher force the next input. That's how you do machine translation with recurrent neural networks. Like this thing is classifying words basically. You're projecting into the vocabulary or the target vocabulary from which you take the maximum probability word and output it. As long as you don't get end of sequence. Once you get end of sequence, you stop decoding. And the input, yes. Yes.
I just started.
No, here this is the memory. So in this output, it basically remembers the whole input sequence. Everything which you need for the translation is in one vector. This is important. Everything you need for translation is crammed into one vector. So it's also like magic, it works. Like, can you cram a sentence into one vector and then just try to decode from this vector? Yes, you can. This is the encoder-decoder architecture. So you pass it on. You update your state by adding more input, and you're just updating your memory, and you keep the memory until the very end. So there's a memory cell, or the memory vector is going from one state to another in the encoder and the decoder. Does it answer your question? So then I didn't understand the question, sorry. Yes. 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 Yeah, we don't care. We just discard it. Doesn't exist. We don't care. There is no loss. There is nothing. There could be output, but if there's no loss, there's no updates in that, and we don't care. Yeah, that's exactly. Okay. Any other question? Encoder, decoder. So let me just go through this. We have the initial input of the decoder is this BOS, so special token BOS. And again, here, just in better detail, is the state, like taking the previous output into the